Ik open de zitting van de commissie ter beoordeling van het proefschrift en de stellingen van Lasse Peters, Master of Science in Mechatronics. A warm welcome to all of you at the public defense by the candidate of the thesis entitled Game-Theoretic Motion Planning for Multi-Agent Interaction. The Board of Doctorates of TU Delft has installed a committee to evaluate the thesis and the propositions. The committee will have a debate with the candidate in public. It's an honor to introduce you to the members of the committee, to whom I extend a hearty welcome. First, Professor Satoretti from the National University of Singapore. A warm welcome to you, although you participate online. Then we have Professor Tumova, KTH Royal Institute of Technology from Sweden. Also a warm welcome for you. Then we move to the other side of the table, Professor Spaan from Delft University of Technology, the Faculty of Electrical Engineering, Mathematics, and Computer Science. Welcome. Then we have Professor Grammatico, also from Delft University of Technology, from the Faculty of Mechanical Engineering. Then we move to this side of the table, and we have Professor Ferranti, promoter, and on my other side, we have Professor Alonso Mora, also promoter and from the Faculty of Mechanical Engineering. Thank you all for taking part in the ceremony. My name is Marja Elzinga. I'm a professor at the Faculty of Architecture, and today I am chairing this session on behalf of the rector of Delft University of Technology. I now request the candidate and the paronyms to take part at the lectern. Waarde promovendus, I kindly ask you to give a short presentation on the content of your thesis. Understandable for non-experts. You should highlight the results obtained, their relevance, and possible applications of your findings. You have exactly 10 minutes for this. The floor is yours.
Dankjewel, mevrouw director. So, to motivate the kind of work that I've been doing in my thesis, whose title we've just heard at the beginning of the session, I would like to start my talk with a rather extreme example of multi-agent interaction. Here we have a human driving along a road, and initially the scene appears quite normal, but then after a few seconds we see a pedestrian running onto the road, and they turn around to pick up something that they've lost, and the driver of this car has to adjust their plan of action to make sure that everyone remains safe. Now, I would argue that the driver in the scene was able to handle this scenario quite well because they possessed a degree of social intelligence. They were able to judge the scenario quite quickly and then adapt their plan accordingly. Now, if we wanted to deploy robots to similar scenarios shared with other decision makers such as humans, then we need them to understand the interdependence between their actions and the decisions of everyone else. This is precisely the kind of problem that I've been studying in my dissertation, and I've been studying it through the lens of game theory. In a game, we model each decision maker in the environment as a player. So if this scene were to take place between a robot and a human, then the robot could be player 1 and the human could be player 2. The decisions of all of the players are constrained to a set of rules. For example, physics may dictate that humans cannot fly, they can only move at a maximum velocity. A car has certain kinematic constraints, it cannot move sideways. And there may be traffic laws. Within these rules, game theory then models each player as seeking to achieve a certain objective, an individual objective per player. So for example, each player may want to reach a certain goal location while avoiding collision with other players and minimizing effort. a game solver takes a mathematical description of these rules in terms of constraints and objectives in terms of cost functions to compute what are called equilibrium strategies. Those are unilaterally optimal decisions, so decisions where no player can further unilaterally improve on their objective. The key advantage of this kind of reasoning is that it provides a robot with a tool for coupled prediction and planning. So if a robot applies this kind of reasoning online, they can make a game-theoretic prediction of how another agent will behave and a corresponding best response plan for the computer, best response plan for themselves, and they're computed jointly in a tightly coupled fashion. And if we apply this kind of reasoning repeatedly, then we can interact with other agents. Now, while this is a very powerful tool, there are several challenges in making this a useful tool for robotics. There are 3 challenges that I would like to highlight. First of all, in robotics, we often don't know the intents of other players a priori. For example, for the human, we didn't know if they want to go left or right. Furthermore, there's a challenge of computational complexity because these games typically involve solving challenging coupled optimization problems online. And finally, there's a problem of modeling effort, so to capture a certain interaction as a game, especially when there are, for example, hard-to-model physics involved. My dissertation has made contributions to addressing each of these 3 challenges, and throughout this talk, I would like to highlight 3 spotlight contributions. The first spotlight contribution relates to the problem of objective uncertainty, which we address by inferring other agents' intents from data. In this setting, we start with the conventional setup of a game where usually we are given objectives and rules and we are asked to find strategies, and we turn this reasoning sort of upside down. We solve the inverse problem, where now we are given observed strategies and we are asking which objectives would explain the observed behavior. If we apply this kind of reasoning to recent observations of other players' decisions, then we can recover their objectives and make predictions about how they will behave in the future. If we apply this kind of reasoning, for example, to this multi-agent interaction problem, then here the robot is able to constantly update their belief about where the human may want to go, and thereby closely follow them without colliding. And the reason, the key innovation that enabled us to do this is that our approach handles partial noise-corrupted observations. So the robot doesn't have to observe the decisions of the human directly. It can only observe outcomes of those decisions, for example, noisy sensor data such as the position of the human. The second spotlight contribution relates to the problem of computational complexity. In this spotlight contribution, we've looked at the inner workings of a game solver and thought about how we can accelerate them. So usually if we solve these games online, we have to solve a quite challenging coupled optimization problem online. And you don't need to understand the exact mathematical formulation that I put on these slides, but I want you to understand that the mathematical object the robot has to reason about online are these continuous trajectories of both of the players. So for example, for the car, different steering signals, different acceleration and braking commands over the next, say, 10 seconds. This is a quite challenging strategy space to reason about online and can take quite some time to find a solution. So instead, in this work, we've simplified the online computation by instead having the players only reason about discrete candidate plans shown by the dashed lines on the right. If we make this simplification, then online, the planner simply, or the game solver simply has to select which of these actions to take based by computing the optimal probabilities for each player, so the equilibrium probabilities. And to make sure that we have candidate plans that adapt to various scenarios, we don't use fixed candidate plans, but instead we train a neural network to propose these candidate plans to find good strategies. And we are able to formulate this learning problem in a way that the neural network learns competitive, state-dependent candidate plans that exactly respect the constraints, so the rules of the game. Originally, we applied this kind of solver to this tag problem, where here the red player learns to tag the blue player, while blue learns to run away. And you can see quite some interesting behavior emerging, where, for example, blue sometimes tries to hide in a corner to get rid of the red player. And they're able to learn this behavior very quickly in this setting, within 2 minutes of interaction. More recently, after I've already submitted my dissertation, my former master's student, Andre, and now PhD colleague, has applied this to a drone racing setting, where here the yellow drone uses exactly the same solver. And because the solver is quite quick, it is able to find competitive overstating overtaking strategies because it can update its strategies within 7 milliseconds. The last spotlight contribution relates to the problem of modeling effort. In this last chapter of the dissertation, we've looked at problems that go beyond collision avoidance. Here we have 2 robot arms that can also be seen as players in a game. And here they are tasked to move, for example, the yellow object to a specific location on the table, maybe to the right end of the table. And a key challenge in these multi-agent manipulation problems is that beyond social intelligence, to coordinate with other players, this requires a degree of physical intelligence. It requires certain skills to handle the interaction with the object, which from a mathematical perspective involves quite challenging physical phenomena. An approach that has become very popular throughout my PhD is to learn these kind of skills from demonstration data. But a key challenge in this multi-agent setting is that collecting this kind of data for multiple robots is expensive because we have to operate all of them at the same time. And we need a lot of data to cover the space of possible things that robots may want to do. So the key idea of this work was instead to learn these physical skills only from single-agent demonstrations, which are much cheaper to obtain. And the key artifact of this kind of learning is that then we have a diffusion policy which enables a single robot to move an object to arbitrary positions on the table reachable by that robot. Our work composes these single-agent policies into one cohesive multi-agent policy by guiding the single-agent diffusion policies with a multi-agent objective, the same mathematical object that you've seen in the previous slides. And by doing so, the robots learn in the setting how to move the cube to the right end of the table, which requires one robot to pick it up, understand how to pick it up, place it somewhere where the other robot can reach it, and then eventually move it to its target. So this concludes the third spotlight contribution, and therefore also my talk. So to summarize the main takeaway of my thesis, by studying multi-agent interaction through the lens of game theory, my dissertation enables robots to infer other agents' intents, find viable strategies efficiently, and coordinate even in complex physical scenarios. This concludes my talk, and I'm looking forward to the questions of the committee.
Thank you very much for being perfectly in time. I would now like to start the opposition, in particular with the committee members online and at the other side of the table. Professor Sartorini, may I invite you to open the opposition?
Yes. Pat Promovendis. So first of all, I'd like to thank you very much congratulate you for your thesis. So I find the document to be very pleasant to read, remarkably well packaged, like a set of chapters that build together very nicely into a story. And I also like the topic, of course. So congratulations for this. But I still have a few questions, and my questions are going to focus, strangely maybe, on one of the last chapters, the one about building those multi-agent strategies from single-agent skills or demonstrations, right? And so one of the first things I have is a small issue with scenarios where you may not be able to find common collaborative strategies because the pieces that compose them are not available in the single-agent data. So for example, if I want 2 robots to carry something that is so heavy that neither of them can carry it by themselves, I'll never have the data from either of them that would allow me to build this, let's carry a sofa together. So my question is, what can you do for those scenarios? Can you extend your approach in those directions, or why did you choose not to be able to handle scenarios like this? Because you mentioned it in the thesis a little bit.
Hooggeleerde opponent, thank you for the question. So, yeah, indeed, so we have been, I agree with your intuition that the approach that we've taken so far would not apply to settings where there's a behavior required that is completely outside the single-agent data, and there's also some theory that suggests that that shouldn't be possible. For example, we wouldn't expect a robot to hand over a cube mid-air, or as you say, maybe lift an object together. When we scoped this contribution, we were really looking into, okay, how far can we push with only single-agent data and a cost? But I do think that, and I think in that setting, I have no immediate reason to believe that we can kind of get this very dense interactions to emerge, or at least I would find it challenging to get there. However, I think there is sort of room for future work where, for example, you think about a good mix of single-agent data and multi-agent data. So I'm a strong believer that now we have all of these really nice tools for learning, maybe even downloading pre-trained single-agent policies, and we shouldn't be doing all of the work again if we now have 2, 3, 4 robots, right? And so we should think about how can we use that. But I absolutely agree with your intuition that if we have some new behaviors where 2 robots, for example, lift an object, we would have to have some multi-agent data as well to sort of complement the data mixture. I think for some of the maybe pushing an object together, you can maybe build some curricula where this can still emerge. But I would also suspect then that the multi-agent dynamics, they suddenly look so different that it's difficult to get make the policy not go out of distribution in that setting. Yeah, so I think it's a very interesting question. What is the right place to use multi-agent data? For example, you can also use multi-agent data to learn the cost function, right? So there's a wide variety of applications there.
I mean, picking back off of what you just said, I agree that I would not expect the math to make these collaborative behaviors appear, right? But humans are pretty good at kind of inferring what could I do with you that clearly I would never do alone, of course, right? So we can achieve this task together. So is there something from like the way we approach problems that we could maybe get inspired by to try to go beyond, like allow agents maybe online to start thinking about adding to their single agent skills to create new pieces that they could combine with another agent?
I think there's room for that, but this, for me, it would be in the regime of speculating. So I think in chapter 7 in the future work, I'm also proposing to investigate more, for example, multi-agent world models, and I suspect that this would be an important component to it, because the key challenges is understanding how now the joint actions will affect the future state. And this is very difficult to sort of get out of a method without any kind of understanding of what even the multi-agent dynamics would look like, sort of some general dynamics where multiple agents can take actions.
That's fair.
So if I could speculate, I would say that the reason why humans are quite good at some of these tasks is that we are able to observe another agent, kind of recover, almost in an inverse game sense, okay, what is the task they're trying to do, but in much more abstract sense, right? Like maybe in vision language action model terms, like we are recovering the prompt that's happening. And that's actually, in literature outside of robotics, some interesting evidence that this is what's happening, that, for example, stroke patients that have damage to the motor cortex, they are no longer able to understand, for example, if their right arm doesn't work, they wouldn't understand if they see someone brushing their teeth with the right hand, what's going on. So there's some evidence that this is what humans are doing. And I think it's interesting to think about what it takes to get that skill to robots as well.
I agree. Yeah. Okay, and then follow-up question for chapter 6. So close to in the results section of it, you discussed this example of a handover of an object. Right? I think it's a glass, right, or a cup, or something like this, between the 2 robots. And you say that there's this new discovered collaboration strategy that seems to emerge, even though the parts that compose it are not part of the single agent demonstrations. And I have a hard time seeing how this would happen again from the math, right, and how the agents are composing those skills together. So is the handover really a new skill that was generalized, or is it just a composition from something that was present in the original demonstration data set?
No, I would absolutely agree with your intuition that there's, so I would have to qualify that statement. I'm not sure where exactly you found it, but the behavior that you would see, also when you run it on hardware, is that a robot will place the object. So the only thing that a single robot has been shown to do is to pick and place objects. And so there's no situation where they would suddenly start picking and place or handing objects over in midair. So the kind of behavior that emerges is that the robot places the object somewhere where the other robot can then reach it to then eventually move it to the goal. And so I would agree with your intuition that this is composition. And it's arguable to which extent this is new behavior, right? Like we've never shown this exact maneuver to both of the robots. And the key challenge is that for both robots to sort of accidentally stumble into that behavior is quite difficult, because the likelihood of that exact maneuver that you need to take with multiple agents, even though the interaction seems so simple, the likelihood is quite rare. So, for example, if you just do rejection sampling on the single agent policies and then you just hope to eventually find this strategy, we were never able to do it, and it's the precise reason why, for example, we had to develop our own guidance scheme.
Okay, that's fair. Yeah. And then last question, again, kind of speculative or turning toward the future. I like the idea of the decentralized skills and then decentralized execution. But again, going back a little bit more towards the human-centric intuition, like we should be able to, conceptually decentralize the execution as well. So do you have any ideas along this direction?
Yes. So I've read your group's work on the latent theory of mind, which is kind of taking the inverse approach, right, where you do centralized training, decentralized execution, and we've kind of have the transpose of that in a sense. Like we have decentralized pre-training and then centralized execution to get the coordination. I think there's room in then eventually distilling that policy again back into some decentralized policy with the exact architecture that you've been using in your work. For example, a naive way of getting there would be to literally just use our scheme to generate a lot of data for just new demonstration data, which is now cheaper to obtain, and then run your approach. But there would probably also be a sort of a shortcut that can be taken without doing a lot of extra work, because some of the score estimates can be reused.
Okay, that makes sense. Yeah, that's good. And then, Mevrouw Director, can I ask you to read proposition 6 from the thesis?
Thank you, Professor Satoretti. Waarde promovendus, may I invite you to read or invite some of your paronyms to read proposition number 6?
Can I ask Natalia to read the proposition?
Model-free approaches are a hoax. Ultimately, every method that works in practice needs a model.
Okay,
Okay.
The floor is yours.
Wait. Do you have to defend, or I can? Okay, so I can answer the question, I think. So I'm surprised by this proposition. It's pretty strong, and I'm also surprised because it's good. It brings debate, right? But if you're looking at big advances in learning that have already seen the light of day, like been either deployed or at least tested in realistic scenarios, right? So you can think of a lot of locomotion policies for quadruped, hexapods, now going into local manipulation with humanoids. But even if you go to something that's really close to being a product, like Waymo's, motion planner, my understanding is that they've gone fully into the end-to-end model-free approach for their full planning stack. So there's still perception, etc., in a modular way, but my understanding is it is pretty much model-free. They would directly contradict this hoax statement, right? So do you want to, comment on this?
Yes, I'm happy to defend that proposition. So I think the line of reasoning when I wrote that proposition is that I think or in that community, we're sometimes dishonest about what it means to have a model. So if you have Isaac simulator where you can simulate, a couple of thousand robots at the same time, and then you use it with a model-free approach like PPO, I would argue you're still using a model. Like none of these model-free approaches that we have so far are data efficient enough that we can just run them in the real world. And so usually all of the methods that end up working is either having a smart physics engine, set it up, and then we can collect a lot of samples. But someone has to build that model, and the reason why we as roboticists get to enjoy that model and call our methods model-free is because someone at NVIDIA sat down and understood the contact dynamics. And I would argue in the autonomous driving setting, of course, we can only speculate what exactly they are doing. So from my interactions with people in that domain, they are building a lot of models, a lot of re-renderings, a lot of sort of local scenarios where they can train their system. And at the end of the day, if you do imitation learning, I would argue then at the end of the day, the driver is the model for which actions to take, right? So does that answer?
Okay, so not really. It brings another question, which is if learning a model and therefore like notions of the model being saved in the weights, because it's kind of what you're saying, right? I learn a model-free system, but because I've learned it through some interaction with the world, I've understood the model implicitly in my weights, right? If this is the case, then there are no model-free methods. So it's not really that they're a hoax, it's that they're just don't exist? Or do you have an example of an actual model-free method that just is not sufficient then?
I mean, I would argue that if you were able to train PPO on a simple real-world problem where you really don't have, like, it is safe enough to do this training in the real world, then I would be happy to call that model-free. And I'm optimistic that maybe one day we will have these kind of methods, but I think what we are currently calling model-free approaches, I would not call it that, because usually they are so data-hungry that you end up having to use a model somewhere. You end up maybe, I mean, what's very popular now is building a world model maybe for a small scene that you care about and then do training in the latent space, but usually just the sampling complexity, the data hungriness of these techniques makes it such that you have to build a model somewhere.
Okay, thank you. I assume this proposition requires much more discussion, but for now, Professor Satoretti, may I ask you, are you satisfied with the answers to your questions?
I am. Thank you.
Okay, thank you very much for the opposition. And then I would like to invite Professor Tumova to follow up with the opposition.
Thank you. Vade promovendus, thank you very much for the presentation and the thesis. I very much enjoyed both. My first question relates to the first part of your thesis, which is on inverse games. Somewhere in the introduction, you mentioned you had a sequence of questions, like what social conventions do the agents in the road follow? So my question is, when you learn the intent, do you capture all of these social conventions, not just intents, but also the capabilities and other aspects than the intents themselves? Or how would you integrate them into your inverse games?
Hochgelehrter opponent, thank you for the nice words. As to your questions, there's several things that I would answer. So first of all, it is true that in the way that we've used inverse games in chapters 2 and 3, we would write down sort of an engineering, like an engineer writes down the cost structure and we just find the parameters, right? And so usually the way that we were handling the cost design there's for the ego robot, we already have a library of cost that we would use to generate autonomous driving behavior, and we use the same library also for other agents. Now, I agree with your intuition that in this setting there may be some social norms that we have not included. For example, we've never made an effort to maybe encourage robots to pass other humans on the right. Maybe if you navigate a crowd, something like that would be important. And then your second question also related to capabilities, right? So maybe, for example, I see a pedestrian pushing a bike. Now, are they a bike or are they a pedestrian? So I have to learn their dynamics in a sense. So to answer those two questions, with respect to social conventions and sort of more subtle things that may be encoded in humans' behavior, I think that writing those down by hand is a bit optimistic. But I do believe, I mean, there's all these techniques now for example, like adversarial motion priors or like generative adversarial imitation learning to recover costs. And so if I suspect that the more subtle notions of social interactions we would have to recover from a more data-driven approach, so at least to get the cost structure. And then as to dynamics, from the perspective of the math, there is no fundamental reason that we cannot also infer parts of the dynamics. We haven't included it in the work at the time because we wanted to have a sort of a simple story where the uncertainty is only about the objectives, but especially in chapter 3, the same math that makes it possible to infer, to sort of pull gradients through this forward game to then update the parameters for cost functions can also be applied to dynamics of other players. Now, a key problem, which I believe is open, is that if you add too many parameters in all sorts of things of this problem, you basically run into an observability issue in the sense that, like, you cannot decide if someone doesn't go left because they don't want to or because they're physically not possible to turn left, something like this, right? And I think I have personally not made any effort to systematically understand under which conditions this sort of observability fails. And I think, I believe that this is an open question.
Yeah, thank you. I agree to a large extent, and I want to keep digging a little bit into this topic of what was and what was not captured by the intent. People also vary. There is variability in their objectives, and you assume to have the cost structure. And then back to the model discussion, all models are wrong, some are useful. So to what extent would you say your model is wrong, and to what extent is it useful, this whole approach of let's learn the intent?
So overall, I believe that this is probably a very domain-specific question, and it remains to be seen depending on the application. The more, so in the game setting, the more we are actually to some sort of strategic interaction, like the drone racing example that I've shown, or the tag, then this is a very good model. And I think there's very little left on the table. Of course, we may not know the exact dynamics. I think driving is one of the ones where it's wrong, but still very useful because there are so many rules that dictate how people have to behave. The closer we go into very unstructured scenes like crowd navigation, if those scenes are heavily dominated by social norms, then I can imagine that at some point the model is still useful, but you're paying quite a high computational cost to making these nice predictions that are coupled with yourself. But because they are wrong in a sense, you may be able to get them much cheaper. Maybe failure is also not all that bad, right? Like if you have a cheap robot, light robot that can bump into humans, is it really a problem if you like, so I mean, so long as you don't harm them, maybe all of the all this heavy machinery isn't needed.
Thank you. That sort of implicitly answered my question also on generalizability beyond navigation here. Unless you want to say something more on where do you see these techniques being applicable more naturally, and where is the limitation? But I assume that you just answered that. So maybe let's move on to chapter 4, which was on contingency games. And you had 3 modeling assumptions there, especially assumption number 2, it felt quite strong to me. So the assumption said that we assume that the robot has access to an estimate of so-called branching time, which models the future time at which additional state observations will be resolved, all uncertainty about the initial unknown theta. Can you clarify how limiting this is? How is it reasonable to assume something like that? Or if this doesn't hold, what can we still take from your contingency games approach?
Yes, thank you. So the original motivation for making this assumption is that actually prior to my PhD studies, I've done some work on, for example, POMDPs, and their QMDP solutions can sometimes be a very good approximation, even though they are wrong. And a QMDP approximation assumes that right after one step you will have certainty. So if I'm recounting correctly how this chapter has developed, is initially we have done exactly that, and we found that this can often be overly aggressive. So the robot would very early commit to an action when they should have waited longer. So yeah, so then we've introduced this heuristic that you've also probably seen in the chapter, where we then estimate the branching time dynamically. So initially we've been kind of looking at, okay, how do different branching times behave, change the closed loop behavior, and the trend is that the higher you choose the branching time, the more conservative the planning is, and the shorter you choose it, the more aggressive the planning is. And so in this work, we have not, we've simply used it as a tunable parameter and said, okay, we can write down some heuristics for estimating this value. But I suspect there's a lot of room for future work where we can maybe estimate this time from some kind of reachability on the belief. But currently, the way that the contingency games work is formulated, you can actually, it would be difficult to kind of infer this value from data directly. So for example, the robot can currently not understand, oh, if I maybe take a certain action, then my uncertainty will resolve more quickly, right? So currently there's no notion of active information gathering in this framework. Does this answer your question?
Yes, thank you. Mevrouw Director, do I have time for one more quick question?
One more quick question, that's fine.
Excellent. Then I would like to ask for reading of Proposition 8, please.
Waar de promovendus? Can you read or have read proposition number 8?
Natalia can read proposition 8.
A key challenge in robotics and in life is knowing what to learn next in order to improve.
So what's the idea to address this challenge? What's the secret?
Unfortunately, I mean, I'm claiming it's a challenge precisely because I don't know the answer. So I think before I even started the PhD, I've left the POMDP world precisely because I felt this problem is so incredibly hard, and active information gathering is just, I don't know how to make meaningful progress on it in the context of the scales that we see it in robotics. But I do believe that it's a very interesting open direction, right? Like in these game settings, for example, in the contingency game work that you've highlighted, there's only one directional uncertainty, right? The robot doesn't know what the human wants to do, but we assume the human knows what the robot wants to do, which is an additional assumption. And so I think getting more of the uncertainty and active reasoning about uncertainty into these frameworks would be a very important future direction of work. And the life part of that proposition relates to the fact that as a PhD student, I always find it very challenging to understand, okay, there's so much literature, especially now that the pace has increased so much in the last few years. Like you have to decide what to read next, and there's a very similar hard problem that no one seems to have a good answer to.
Okay, thank you. Professor Tumova, are you satisfied with the answers to your questions?
Yes, I am satisfied. Thank you.
Thank you very much for the opposition. And then, Professor Spahn, may I invite you to continue the opposition?
Dank u, mevrouw director. Waarde promovendus, thank you for your thesis and the presentation. It was very clear. I wanted to start with page 1, which, no, you don't need to pull up, I think it's fine, where you kind of define what an agent is. Right, and you seem to limit yourself to humans and robots. So what about software agents?
Hooggeleerde opponent. I think, so the scope of the thesis was exactly about these sort of physical motion planning problems, but I do believe that there's a lot of room for applying sort of game-theoretic reasoning to a lot of these software agent settings. I mean, to speculate a little bit, in my view, human interacting with a large language model, the discussion is also a game. It is a sequential game, and there's sort of some very different dynamics underpinning it, but technically there is something to be learned from kind of reasoning about, okay, how does my response now change what the other player will say? So I would, philosophically, I would say, these sort of this multi-agent reasoning totally extends beyond this human-robot interaction setting.
Right, and what about AI agents that go out and do try to achieve stuff in the world, which is more and more happening?
Yeah, so I mean, the general idea in the thesis would have been that if there's any other decision maker in the environment that is not just dictated by physics but by some active decision making, then I would argue they should be modeled in this game-theoretic framework. Maybe a closely related challenge that I don't have a good answer to, but I think that relates to the Chapter 7 discussion of model order reduction is how do you even decide who is an agent? Like, if I'm entering an intersection as a human, I don't think, and I'm speculating here, I don't think I'm ever actively thinking about more than 3, maybe 5 people at the same time, right? So I'm making an implicit decision about, okay, for these few seconds now, I will handle maybe these people that are quite close to me or those people that I can predict will be close to me in the near future as agents, and others I have to abstract away because I can't sort of reason about everyone closely. And I think going forward, it will be interesting to see where we draw these boundaries when there's maybe many decision-making agents around a robot, and where do we even do this cutoff.
Okay, thank you, that's clear. Let's move to page number 2. So I was very interested to read that you write something there like, if the reader happens to be human, right? So I hope all of you read it. We're human, we enjoyed reading your thesis. But it seemed to imply you were also writing your thesis to be ingested in a public data set, which would then be used for large language models, etc., be trained on. That got me thinking, what do you think would be the most salient part of your thesis for such models? What could it learn from your thesis?
So, well, maybe to contextualize, I've written chapter 1 to be accessible by a very broad audience, and I wanted it to be a little bit playful so that it's not scaring off any reader before they reach chapter 2 and beyond. There was some kind of internal bet to put a sentence like that into the thesis. More generally, I would say that I forget. I think this statement in this particular context related to the fact that there are some evidence, there's colleagues at TU Delft even who have used, for example, vision language models to maybe get a feeling for what the preferences of humans are, right? So there is some evidence that that this understanding of what is a good interaction, it has already leaked into language models to some extent. Like there's, I forget the name of the work, but like, yeah. So, and I think from the thesis itself, I think the high-level idea that I would like to take a reader away, even if they don't end up applying game theory exactly, is that I think it's important to really reason about these decisions as equilibrium problems. There was a really nice work a few years ago from ETH on, for example, playing games with prediction models, where you kind of search for an equilibrium over prediction models, which is something you may, for example, do to get an iterated best response scheme for maybe a conversation in a language model. So in general, I would say that these ideas that that game theory kind of has underpinning that, okay, everyone's decisions, you cannot predict what someone else will do. You will have to really understand, okay, I make a prediction given my current actions, but then when I change my action, this prediction will also change. This is the main thing that I would hope leaks into the general knowledge on the long run in robotics, but then probably by proxy also into these public databases.
Okay, clear, thank you. Then let me continue where Professor Tumova left off in chapter 4, the contingency games. She was asking about assumption number 2. I was triggered by assumption number 3, which says something that the belief is assumed to be fixed. What does that mean exactly?
I would have to double check,
Yeah.
sorry.
I think it's page 65.
Yeah, so the underpinning assumption here is that the belief doesn't change as basically we have a fixed uncertainty throughout the entire window. Technically, if this was a dynamic game, we would understand, okay, now we took an action, we get a new observation, and the belief is also dynamically evolving together with the state, right? Like here in this work, we are pretending that we have a belief over these different hypotheses, maybe 50% the human going, or maybe 70% the human going left and 30 going right, and we are not updating this belief as we're making decisions in the game, because otherwise we would get much closer to the intractable problem of, for example, a partially observed stochastic game.
Right, I see there's a tension between modeling as a partially observable stochastic game and not, I guess. But do you think, is this reasonable here? I mean, so there's no notion of information gathering or perhaps weighting, as you indicated before, right? Sometimes weighting gives you more information, and that would help you to get a better belief.
So I should clarify that, I mean, we do update the belief on the outer loop, but there's no active interaction between the planning and the decision making, right? So every time we with this heuristic, we update our branching time, we would take an action, we get a new observation, we get a new belief. The way that this belief changes is not understood by the game a priori. It basically just reacts to the belief changing over time. So this belief update happens on an outer loop. In this particular setting, anecdotal evidence is that we've built some GUIs where, for example, you can mess with the robot, where you can like send the human left, right all the time, and the robot will just decide to wait it out because of this heuristic. But this is an emergent behavior of how the contingency game interacts with the way that we estimate the branching time and the belief update. We haven't explicitly encoded or modeled this anywhere, and I do believe that it would be very interesting, even though I don't have an explicit answer how to do it, to get the contingency planning to actively understand how their decisions will change the belief in the future.
Right, so did you consider modeling this as a POMDP with kind of a fixed model for the human based on their true intent or something?
No, in this work we have not considered that because we were precisely thinking about, okay, how can we get this contingency reasoning to games? I agree that there would be sort of a non-game version of this where now the prediction has to come from some otherwise written down model. My view on this generally is in a game the prediction, the mathematical object that makes predictions about others just happens to be an optimization problem, which depends on your own decisions. In some settings, it is conceivable to replace that module with maybe a closed form approximation. Sometimes we have a neural network that's maybe can make an ego condition prediction about how someone else will behave, right? So maybe I have a neural network that takes in the current state and my sequence of future actions to make a prediction of how that other agent will behave given my action. I would see that, in my view, that's an approximation of the thing that's, of the game that's actually going on. And so I suspect so far, if you want to get closer to this active information gathering, because POMDPs are already very hard in my understanding. I mean, if we have no idea how to solve it there, I have no reason to believe we can anytime soon get this into the game itself. Okay. So I would argue that is a good use of an approximation in that setting.
And then what if you, so okay, let's assume you have these rules, we solve it, we have equilibrium strategies for both the, let's say, the vehicle and the pedestrian here. So the vehicle can run this, right? Can solve it and come up with these strategies. The human probably is not doing that. The human was just busy trying to not get hit by cars or pick up a phone or whatever they dropped. So this assumes they also have a similar kind of modeling, that they're rational. There are all kinds of underlying assumptions there that might work well in these simple settings, I would say, but in more complex ones, I could imagine them breaking down more easily. Do you have any thoughts on that?
Yeah, so, I mean, this is, I would say, for me also in the regime of speculation, because it really depends on the application. In the hardware experiments that we did run, I've been consistently surprised of how good of a model it is of the human. I mean, I mean, arguably, it's a simple setting, this collision avoidance task that I've shown in the talk, but I think it's, again, a case of all models are wrong, some models are useful. The reason, I mean, now this is a matter of taste, perhaps. I often find it easier to express the kind of rules that I care about in optimization, where I can really write down a constraint and I don't have to pray for some neural network to enforce that constraint. So in that sense, I think that's where the benefit of these methods comes from, is that we can have with fairly little data, because we have so much structure, we can already make some predictions and enforce certain rules. I think if you are in a domain where data is abundant and you have so much you have so much data and knowledge of how to engineer these systems, eventually the game maybe doesn't add a lot. I think that the game theory is particularly interesting for these settings. That's also why more recently I've been pushing into these hard two-player interactions like the manipulation setting, which I'm very interested also to explore towards the postdoc, is that I think whenever we have infinite data, like in autonomous driving, a lot of things work because we have many ways of processing a lot of data now. Whenever we are in this low data regime, then additional inductive biases are necessary. And then I think game theory provides a really interesting sort of way of structuring the problem and getting a lot out of little data.
Okay, thank you.
Professor Spahn. Are you satisfied?
Yes, I am.
Okay, thank you very much for the opposition. And then, Professor Grammatico, may I invite you to continue the opposition?
Thank you, Meneer Director. Waarde promovendus, I was pleased to read your thesis and very much pleased to see application of game-theoretic control principles to robotics. I have some questions, and I would like to start from chapter 2, and specifically from the definition of open loop Nash equilibrium, which is around page 16. I should say page 19 for the actual definition 2.1. Yes, so here you call this equilibrium in equation 2.7 as open loop Nash equilibrium, and I suppose it refers to the game in equation 2.6.
Yes. Yes.
My question is, since you use this keyword open loop, and therefore you refer to a dynamic game, where do we see the dynamics in the game played in equation 2.6?
Okay. Hochgelehrte opponent, thank you for your for your kind words and for the question. So there's a few things here. So equation 2.6 does not actively or does not capture dynamic information, right? So here, a player really, like, from a perspective of game theory, this is a static game. So effectively, a player commits to the next, say, 10 decisions a priori, and from the perspective of equation 2.6, there's no understanding that there will be replanning in the future. So we apply this to a dynamic game in the sense that we end up observing a dynamic interaction where replanning does happen, and we use this approximation just to make it tractable. I do have follow-up work with Professor Friedrich-Kahl from Texas, where we explicitly try to capture more of the feedback dynamics also in the inverse games, but we did not do this as part of the thesis. So this is a contribution that's mentioned towards the end of the introduction that goes beyond the thesis itself. Okay,
excellent, I agree. My next question is still on chapter 2 and specifically on the equilibrium condition 2.8 and later on summarized in 2.12, because I noticed that those conditions are non-variational, meaning that you don't assume limitations or restrictions on the dual variables lambda, which generates non-convexities, or I should be precise, non-monotonic operators. Could you comment on this design choice?
I believe, so this modeling choice has evolved throughout my thesis, and this chapter is one of the oldest papers that I've submitted. So more recently, it's certainly true. For example, in chapter 3, I know that it's true that we are sharing multipliers for shared constraints between players, and then we would find a refinement so that actually this is, so otherwise we end up with this continuum of equilibria where, like, you don't really know how collision avoidance responsibility in this particular case would be distributed across agents. So by sharing the duals, you're effectively making sure that everyone has the equal collision avoidance responsibility. I believe this is what we did here already, and I suspect it is described implicitly in the experiments, but I don't think I can figure this out on the fly.
Okay, thank you. Then indeed I would like to move to chapter 3. And I would like to discuss about algorithm 1, which is around page 49.
I don't see algorithm 1 of
53.
Okay.
So the section starts before, but the algorithm itself is on page 53, top of the page. Yes. I have two questions around algorithm 1. The first one is about this solver, solve diff MCP, because MCP stands for mixed complementarity problem. and those in general might be NP hard and yeah, possibly non-monotone, non-convex problems. So what was your approach to make this step in the algorithm numerically tractable?
So I agree with your intuition that in general we wouldn't expect this to be numerically tractable. And we have not made any explicit efforts in this work to, for example, enforce monotonicity of the operators or any of the other assumptions that gives you stronger guarantees. Instead, in this work, we've taken a more empirical approach where we just report the number of failures, and we observed that in this particular setting it wasn't of particular concern. I have been pleasantly surprised overall. So in this work, we've been using the path solver for mixed complementarity problems, which is a very old implementation in C. And I've been surprised when we ran into it. You can kind of see that I became a fan of it when we ran into it. And it's now underpinning a lot of the methods, including the contingency games. And that solver happens to be in practice for the games we care about to work quite well. Even for more modern implementations of, for example, the tag problem that you've seen in chapter 5 also now uses that solver. I think in the future, of course, I think it would be very interesting to combine the work that we've done in this thesis, where we are really not making any explicit attempts of figuring out how to make these games solvable reliably, and combine them with, so instead of just quantifying how often it fails, explicitly make efforts to make, for example, these games monotone or locally always regularized so that we can always ensure existence or a fast solution. Another more engineering answer is that this solver is very old, it's very single-threaded, not using any of the modern hardware features. I think there's, irrespective of sort of algorithmic convergence speeds, there's a lot of room for exploiting modern hardware, exploiting GPUs, and we've started some efforts also with Professor Friedrich-Keil on this direction to sort of figure out, okay, how can we get these solvers onto the GPU? Because I think there's a lot of the tech is very beautiful and was way ahead of its time, but is now kind of could be renovated.
In fact, my other question was, which directions do you see in order to claim some sort of convergence guarantees under certain technical assumptions? And I hear you have already given a couple of directions.
Yeah, so I should clarify that I'm not an expert in the more sort of formal approach to game theory. And my best understanding currently would be that, if you have sort of some additional assumptions on the cost structure, like potential games or monotone, so if the pseudo-gradient of the stacked costs is monotone and the underlying set is convex and compact, then we can sort of say something about the existence, and we can make some more stronger guarantees for how we can find them. I think in robotics, at the end of the day, even something as simple as collision avoidance is very difficult to convexify, right? So I think if we wanted to do game-theoretic planning with more guarantees in motion planning, for example, one of the lines of work I'm very interested in the single-agent domain is this graphs of convex set line of work from Russ Tedrick's group at MIT. And they get some really tight sort of convex approximations of the otherwise non-convex global problem. And I know that the group in Texas, they have sort of looped that single-agent solver into, for example, an iterated best response scheme, but then we know again that iterated best response only works for very specific classes of games. So I think there's a lot of room for thinking about how can we get more global solutions. Like, this is of course a slightly ill-posed question, but I think a lot of the interesting decisions in the game are currently still left to some sort of outer loop, right? Like we are, sometimes the seed in which we initialize the solver will dictate whether we end up passing a player on the left or the right. We cannot make the game solver actively reason about it. So some recent work we've submitted was, for example, on partitioning the space with homotopies in a more heuristic way, which is a particular solution that works well for these motion planning problems. But then in the more general interaction setting, I have no good idea of how we would get there.
Okay, thank you very much.
There is little time for a next question.
Yes, I would like so, if possible. Would you think inverse game theory could be used as an internal model principle.
Hey, thank you, Madam Beadle. I invite the promovendus and his paronyms to take their seat in the audience again. So the committee will now withdraw for further deliberation in the committee room. So this session is adjourned.
Okay, let's go.
Okay. I reopen the session and request the promovendus and his paronyms to take the place here in front of the table. Het college voor promoties van de Technische Universiteit van Delft, vertegenwoordigd door de hier aanwezige commissie, heeft, na kennis te hebben genomen van uw proefschrift met stellingen en na uw verdediging daarvan te hebben gehoord, met de inachtneming van het bepaalde in de wet op het hoger onderwijs en wetenschappelijk onderzoek, besloten u de graad te verlenen van dokter. Ik verzoek de promotor, door het college van promoties als zodanig aangewezen, zich wel van de hem opgedragen taak te kwijten.
Uit kracht van de bevoegdheid bij wet toegekend aan het college van promoties, verklaar ik als promotor namens dat college, hier vertegenwoordigd door de rector magnificus en de overige leden van de commissie, bij deze u, Lasse Peters, te bevorderen tot dokter en u alle rechten te verlenen, welke aan de doktertitel zijn verbonden. Ten bewijze hiervan overhandig ik u het diploma dat u het recht heeft de titel dokter te voeren, ondertekend door de rector magnificus en de promotoren en voorzien van het zegel van de Technische Universiteit Delft.
Okay. So it's the promoter's privilege to be the first to congratulate the young doctor, Professor Ferranti. The floor is yours.
Thank you, Meneer Director. Dear Dr. Peters, dear Lasse, it's a real pleasure and a privilege for me to be the one that congratulates you first with the title of doctor. So I had the opportunity of working with you together with Javier. And from the very beginning, it was clear to me that you were a really outstanding PhD candidate. What impressed me the most earlier on, that you had a really clear vision for what you wanted to do. You made the deliberate decision to move to TU Delft because you wanted to work in an environment where you could interact with more people on motion planning and control. And that showed a lot of courage and direction. Whether we fully met the expectations, I don't know. I cannot say, but I can say that you graduated brilliantly, so you did really well, so I'm really proud of it. You made our groups better. You gave us open, constructive feedback on very important organizational matters for both our teams. And that is something that we will keep with us for the future. You contributed to our education program, for instance, in the planning and decision-making course, and you supervised good master students that continued also in academia. And that's probably because you gave them a really positive example. You have a large network of collaborators. I checked on Google Scholar, I counted more than 20 co-authors, which is a lot. You gave guest lectures both at universities and at companies, which shows, I think it says a lot about the quality of your work and also the relevance of your work that is quite unique at the level of a PhD. You were really independent And for me personally, it was a real challenge to supervise you from the technical perspective, because I often felt that I was learning from you rather than the other way around. So I always had to remember that you were a PhD candidate and not already a senior researcher for the level of maturity and the depth that you brought into our meetings. You have a exceptional scientific record. You published in top robotics journals and conferences. I don't have the time to list them all. You became one of the RSS pioneers in 2025. Your contingency game was also recognized as a finalist from the TC on robot control. Now you will start a postdoc at UC Berkeley, and I know that you want to continue your academic path as a professor. And I really hope that you will keep this dream alive, either if it's not in the US, perhaps back in Europe. Because I think you have the quality to be a great professor, and students will benefit from you. Berkeley is lucky to have you. We have been lucky to have you working with us for the past 4 years. Congratulations again, Dr. Peters.
Okay, Dr. Lasse Peters, you now have the right to use the title of doctor. And your doctorate means that society can rely on your judgment, that you act transparently, and that you independently communicate your results and the social relevance of your work. In other words, your doctorate implies academic integrity. I wish you much success with the responsibilities that come with your new status. On behalf of the Board of Doctorates of Delft University of Technology, I congratulate you, your family, your paronyms, on earning the doctoral degree. So, Dr. Peters, you now may return to your seat, and also the paronyms. Ladies and gentlemen, I thank you very much for your presence, and I hereby close this academic session.